In this mechanism, what we are going to do is show how to make a trans-alkene from an alkyne. So first off, I'm going to start with an internal alkyne. And the conditions for a reaction like this would be sodium, metal, and ammonia. Now be very careful that you don't seem to think that it's NaNH2. We do not want Na+. That is a different version of sodium. That's got its electron removed. We want the sodium that has the electron. And that's absolutely critical, that the sodium has its electron. Now I'm going to, on the next slide, draw this triple bond in a different way so that we can see the orbitals and where the electrons are in those orbitals. It's very critical because you need to remember that orbitals can have none, 1, or 2 electrons in them. So I'm going to try to show things with orbitals on top, and on the bottom just show the electron pushing mechanism. So if I want to see this with orbitals, I'm going to draw out the p orbitals on this carbon system. One of them I'm going to draw in blue. The other one I'm going to draw in red. And this one should be coming in and out of the page at you. I just can't quite draw it that way. Okay? But that would be the triple bond that we're talking about. Again, the same way of looking at that in our normal convention for mechanisms, but just to be showing that triple bond here, like this. So I should be aware these mean the same thing. Now, sodium, I'm going to draw it up here on the top, has 1 electron in its valence shell. If you're just using Na, it's very important you realize that it has an electron. The whole reason you normally see sodium as Na+ is because it likes to get rid of its electron. And that's what it wants to do in this case. It wants to dump off its electron somewhere. I call it the dump off my baby electron syndrome. Okay, we don't want our baby electron. Somebody else is going to have to deal with it. And it doesn't matter which of these 4 p orbitals gets it, but somebody's going to take baby electron. And it's 1 electron, so you use a single-headed arrow to show its movement. So if I'm doing it down here, okay, I'm going to show somebody taking it. As a result of that, a pi bond is going to break. So one of these electrons pairs up with it, the other one hangs out by itself. So you're breaking a pi bond. So I would show that here with 1 electron going one way and 1 electron going the other way, because you're breaking the pi bond. So if I'm showing this with orbitals, that's going to change the hybridization of these carbons. Okay, I am going to draw in the double bond at this point in time. But these have now become sp2 hybridized. And they want to get as far away from each other as they possibly can due to electron repulsions. Now we have an Na+ over here, okay? If you want to draw it this other way, it's just fine. Just drawing the same thing above and below. Draw 1 right there and 2 there. This is called the radical anion, but these carbons literally are now sp2 hybridized due to the fact that we've dumped an electron into one of those p orbitals. It changed its hybridization from a p orbital to an sp2 hybrid orbital. And it's now got a negative charge. Now if you look at your pKa table and look at the bases, because this is a base now, it's got a negative charge. This would be the corresponding conjugate base of an alkene. If you look at the pKa of an alkene, it's around 45. They're terrible acids. So this is a fantastic base. I mean, it is awesome. There's only one base stronger than this, and that would be a deprotonated alkane. So this is an awesome, awesome base. And our solvent here is ammonia. Normally ammonia is never an acid, but in this case its pKa is such that it's going to be a proton donor. Ammonia has a pKa of 36, so this is favorable acid-base chemistry. this pair of electrons will come in here and take the hydrogen, and as that happens, the hydrogen-nitrogen bond will break, and nitrogen will take those electrons with it. And I am using double-headed arrows here because this is 2 electrons that are moving. And you can again do this from the bottom as well. It's just as good. So if I want to do it here, I just take the hydrogen, give the electrons back. Alright, so what do you get as a result of that? Well, you're going to make a radical. Okay, we still haven't taken care of that radical, but we've now given ourselves a hydrogen in one of these locations. And the reason this doesn't ever do anything but what I am showing you is because you still have a pi bond. You cannot rotate pi bonds, so they're stuck in place once this has occurred. It doesn't have anywhere else to go. But it's still a radical. It needs another electrons. And there are more sodiums in there. So another sodium comes in and says, hey, you can have my electron and we can be buddies. So we're going to be buddies. As a result of that, we make another anion. And it is, again, the corresponding conjugate base of an alkene, so it's a really, really strong base. And our solvent in this case is still ammonia. Okay, there's the sodium hanging out there to balance charge. But this guy is a strong enough base that he can remove the hydrogen off of another ammonia solvent molecule. And at the very end, you have made a transalkene because you can't rotate that pi bond. And it tends to just react with the 1 double bond. It doesn't react with 2, and voila, you've got this alkene.